Hello students, I am Satitrakar. Welcome to Class Physics. We are continuing chapter number 2, Electric Potential and Capacitance. In previous lectures, we have discussed different concepts on capacitor and capacitance. Okay, so what's a capacitor? Capacitor is a device which stores charge in the form of electric potential energy. Capacitor is a device which stores charge in the form of electric potential energy. Okay. So what's the difference between a battery and a capacitor? Okay. This is a battery. Battery has positive and negative terminal. Okay. Positive terminal may be treated to be at high potential and negative terminal is at low potential. Between high and low potential difference is V. So battery, if a battery is connected in a circuit, closed path of circuit, then charge is flow, means as we have already discussed, conventional charge flows from high potential to low potential. Okay. If a battery is connected in a circuit, closed path of conductor, circuit, closed path of conductor, a conductor is connected between positive and negative terminal, then as we have discussed, conventionally charge flows from high potential to low potential, but practically electrons flow from low potential to high potential or from negative to positive. Okay. So in general way we may say charge flows from high potential to low potential. Okay. Again, to move the charge, energy is required, because if we take a closed path of circuit by using connecting wire, the connecting wire has resistance. Okay, resistance means the opposition to the flow of charge. When electrons flow, we know conductor has a high number density of free electrons. If a conductor is connected between terminals of a cell, then free electrons tend to move from low potential to high potential. As the number density of free electrons in a good conductor is very high, so the electrons collide among themselves, means electrons collide with electrons, as well as the free electrons collide against positive charge and atoms, thus in the result energy is lost. Okay, so to overcome the resistance, to overcome the opposition, we need energy. That energy is supplied by cell, okay, or battery. That energy is supplied by battery. So battery, in usual way, we do say battery contains chemical energy. When a battery is connected in a closed path of circuit, then chemical energy is converted to kinetic energy of the charge carriers. And when charges move in a given direction, then we do say current. Means current is rate of flow of charge, amount of charge flowing per unit time. We'll discuss in brief in electrodynamics or current electricity. So battery contains energy which helps the flow of charge from high potential to low potential, as we have taken in our convention. Similarly, if we take a charged capacitor, this plate, charge given to this plate is plus Q and induced charge on the second plate is minus Q. So this is at high potential, this is at low potential. Potential difference between the plates of capacitor is V. When the capacitor is charged, it stores electric energy. Okay. When a capacitor is charged, it stores electric energy. Battery has energy. Okay. A charged capacitor also has energy. So a charged capacitor behaves as a battery or cell. A charged capacitor behaves as battery or cell, since there is a potential difference between the two plates of the capacitor. Thus, energy is stored in the capacitor, charge is stored by the capacitor, so energy is stored in the capacitor. So capacitor behaves as a battery or cell. This is basic concept. So in this lecture, we will discuss redistribution of charge. Again, Let's analyze about redistribution of charge. The basic concept you know. Suppose two bodies. This is a body and this is another body. Okay, there are two bodies. I will not hold it in my hand because it will flow through my body, because human body is good conductor of electricity as well as heat. Okay. So we have put these two bodies on insulating surface. Okay. This body is at high temperature. This body is at low temperature. This body is at high temperature. Temperature of this body is high as compared to temperature of this marker pair. Okay. Let two bodies are brought in contact now. Two bodies are now brought in contact. Then what will happen? If two bodies at different temperatures are brought in contact, then heat will flow from hot body to cold body. Hot means the body has high temperature. Okay. If two bodies at different temperatures are brought in contact, then heat will flow from the body at high temperature or hot body to the body at low temperature or to cold body. So heat flows from hot body to cold body till temperature of the bodies becomes same. So heat flows from the body at high temperature to the body at low temperature till temperature of the bodies becomes same. Okay. So where there is temperature difference and there is contact between the bodies, then heat flows from hot body to cold body till temperature becomes same. So if heat is given, then temperature rises. If charge is given, then potential develops. Heat is cause, temperature is effect. Heat is cause, temperature is effect. Charge is cause, potential is effect. Okay. Heat flows from the region of high temperature to the region at low temperature. Similarly, charge flows from the region of high potential to the region of low potential. Of course, we have, as in the conventional flow of charge, practical flow of charge is flow of electrons. Okay. Conventionally, equal amount of positive charge, equal quantum of positive charge flow from high potential to low potential, but practically free electrons move from low potential to high potential or from negative to positive. Okay. So temperature, difference in temperature, there is flow of heat. Difference in potential, there is flow of charge, but with a conducting part. Okay. So electric current, electric charge can't flow through insulators. Okay. So for flow of charge, we need a conducting part. Okay. This is the basic concept. So now we will discuss on redistribution of charge. Okay. Redistribution of charge. Of course, we may consider two capacitors or even two charged bodies. Okay. We know capacitance means capacity to hold charge. Even a single body can behave as a capacitor, but we have discussed a single body is not used as a capacitor because a single body requires a large space but gives small capacitance. But a single body may be treated as a capacitor if it has some surface area, and surface area means capacity to hold charge on the surface. We are discussing about conducting body. Okay. Let's consider two bodies. Okay. So these two bodies are kept on an insulating stand. This is insulated stand and this is also insulating stand. Okay. Because if the bodies are kept on ground is good conductor. If the body has some potential, then charge will flow. We have discussed already all the concepts in potential. If the body is positively charged, then electrons flow from earth to the body. If the body is negatively charged, then electrons flow from body to the earth to make it neutral. Okay, earth is always considered to be at zero potential. Anybody in connection to earth, in contact with earth, also attains zero potential. Okay, as we have discussed. Okay, these are two bodies kept on insulating stance. Okay, charge on this body is Q1, capacitance is C1, potential is V1. Left. This body is a body A, has charge Q1, capacitance C1, potential V1. Similarly, this is body B. It has charge Q, capacitance C2, and potential V2. Or you may take like this, you may take like this. This is a parallel plate capacitor. Capacitance is C1. Charge given to this capacitor is Q1. This is positive plate. Charge given to the positive plate, and this is negative plate. Also induced charge is minus Q1. Okay. Potential difference between these two plates is V1. Of course, we are using R3. Then potential of this plate is 0. Potential of this plate is V1. Okay. Induced charge minus Q1. So potential difference is V1. Similarly, we may take another capacitor of capacitance C2. Charge on this capacitor is Q2. This is minus Q2. Okay. Now this is R3. Okay. This is the common point which is R3. Then potential of this plate is also 0. Left. This potential difference is V1. Capacitance is C2. Let potential of this plate is V1. V2. Then potential difference between these two plates is V2 minus 0 is V2. Now circuit is open. Okay. So what will we now compare? See, in both cases, you may compare both the cases, the similar cases. Sit left. V1 greater than V2. This is capacitor A. This is capacitor B. This is body A. This is body B. This is capacitor A. This is capacitor B. Okay. So the similar notations are taken: Q1 C1 V1, Q1 C1 V1, Q2 C2 V2, Q2 C2 V2. Okay. Let V1 is greater than V2. Body A is at high potential and body B is at low potential. Similarly, capacitor of capacitance C1 is at high potential and this capacitor is at low potential. Okay. Now let these two bodies are joined by the help of a conducting wire. These two bodies are joined by the help of a conducting wire, or you may consider now the circuit is closed. Now switch is closed. Then this becomes a closed path of circuit. And here a conducting wire is connected, the similar thing. Then as we know, if two bodies are at different potentials, V1 is greater than V2, V1 is greater than V2. If two bodies are at different potentials, are brought in contact by the help of a conducting path or conducting wire, then charge will flow from the body at high potential, A is at high potential, to the body at low potential. Charge will flow from the body at high potential to the body at low potential. Here also, charge will flow, conventionally charge will flow from capacitor A to capacitor B. Okay. Charge flows from high potential to low potential till potential becomes same. Okay. Now charge flows from body A to body B till they attain a common potential, or in this case, both the capacitors attain a common potential V. Okay. Charge flow continues till both the bodies or both the capacitors attain a common potential V. Now charge is distributed or charge is shared. Okay. Charge is redistributed or charge is shared. The redistribution of charge, or we may say redistribution of charge, or we say sharing of charge. Redistribution of charge or sharing of charge, if the bodies are brought in contact, then charge is shared. Charge flows from the body at high potential to the body at low potential. Okay. Let V is common potential. Okay. Here we may take V is common potential difference. Okay. V is common potential difference of capacitor C1 of capacitors A and B, or capacitance C1 and C2, the same concept. Okay. Now, we use either of the diagram. Either we will consider two bodies or two capacitors. Okay. Well, now, V is common potential of the bodies. Charge flows from body A to body B. Body A is at high potential, body B is at low potential. Charge flows from body A to body B. Till potential becomes same potential is V. V is called as common potential. Then our aim is to find expression for common potential. Okay. So V is common potential. So V is equal to total charge. See, capacitance is equal to Q by V. V is equal to Q by C. So V is common potential. Q is total charge. C is total capacitance. Okay, or equivalent capacitance. We may write equivalent capacitance. Total charge divided by total capacitance. Total capacitance, we may write equivalent capacitance. Then total charge. Total charge Q1, Q2. We have taken both the charges positive. Both the charges positive. So Q1 plus Q. Total charge is Q total is Q1 plus Q2. And total capacitance or equivalent capacitance. See, now V is common potential of the bodies, or V is common potential of the two parallel plate capacitors. When potential becomes same or potential difference becomes same, then obviously we'll calculate equivalent capacitance of C1 plus C2. Okay, we have discussed about parallel grouping of capacitors or parallel combination of capacitors. In parallel combination of capacitors, all the capacitors are at same potential. Means all positive first plate of all the capacitors are connected to a common point. Negative of second plate of all the capacitors are connected to common point. So potential difference between the plates of all capacitors is same. Okay, this is our basic concept. So, since both the bodies or both the capacitors are in a common potential, so equivalent capacitance is C1 plus C2. This is formula for common potential again. C is equal to Q by V and Q is equal to CV in general. Q1 is charge on body or capacitor A. So common potential may be, in place of Q1 we may write C1 V1, in place of Q2 we may write C2 V2 divided by C1 plus C2. This is formula for common potential. This is formula for common potential. Okay. So numericals on the basis of this formula are very easy. Okay. In general, it may given a capacitor of capacitance 3 microfarad. Okay, everything is given. Potential V1, let 10 volt, is connected in parallel to another capacitor of capacitor. Let this is 10 microfarad, and potential or potential difference between the plates is 1 volt or 2 volt or 4 volt. Okay, then find common potential. Then just use the formula. Sometimes it may be asked. Sometimes it may be asked like this: a capacitor of capacitance 10 microfarad of potential V1 above this body or first capacitor of potential let 100 volt is connected to another capacitor of capacitance 5 microfarad which is uncharged. A charged capacitor of capacitance 10 microfarad and potential 100 volt is connected to another capacitor of capacitance 5 microfarad and the second capacitor is uncharged. Then find common potential. In that case, you will take V2 is equal to 0. For a charged capacitor, there will be potential difference between the plates. For an uncharged capacitor, potential difference is 0. So if it is asked, a charged capacitor is connected with uncharged capacitor, then you should take potential of uncharged capacitor is 0. Accordingly, put here 0. Okay. Then another form of numerical. This is the formula for common potential. Okay. This is the formula for common potential V is equal to C1 V1 plus C2 V2 divided by C1 plus C2. Okay. This is formula for common potential. So let's consider two spheres. Let's consider two spheres. Potential is V1, it is given. Okay. Potential is V2, this is given. Okay. Radius of the sphere R1 is given and radius of the sphere R2 is given. If V1 is greater than V2, now the bodies are connected by the help of conducting wire. Then what is common potential? Formula for common potential. See, common potential is C1 V1 plus C2 V2 divided by C1 plus C2. For a spherical body, capacitance of spherical capacitor is 4 pi epsilon naught r. Okay. So for this body is A, this body is B. For body A, capacitance is C1, so capacitance is 4 pi epsilon naught R1 into V1 plus C2, 4 pi epsilon naught R2 into V2 divided by C1 plus C2, C1, 4 pi epsilon naught R1 plus C2, 4 pi epsilon naught R. 4 pi epsilon naught, all these are cancelled. Then common potential is V, that's equals to R1 V1 plus R2 V2 divided by R1 plus R. Okay. If spherical bodies are given, no need to calculate capacitance C1 and C2, just use this formula R1 V1 plus R2 V2 divided by R1 plus R2. Okay. So, redistribution of charge or sharing of charge. Charge is shared between the bodies and finally the bodies attain a common potential V. But the initial charges were Q1 and Q2. So this is C1, this is V1, this is C2, this is V2. And if they are connected, then they attain a common potential V. Okay. Then this charge Q1 and this charge Q2, after the bodies attain a common potential V, then charges are already redistributed. Then how can you find charge? Similarly, how can we may find capacitance using the general formula C is equal to Q by V, V is equal to Q by C. C is equal to Q by V, V is equal to Q by C. So, you may write, see, here potential is same, V is constant, okay. When the bodies attain common potential, then potential becomes same. Then what we may say? V is equal to Q by C. If potential is same or potential is constant, if V is constant, then Q by C is constant. If V is constant, then Q by C is constant. Then we may write Q1 divided by Q2, or you may say Q1 dash Q2 dash is equal to, you may write like this first. This implies Q directly proportional to C. Okay. So Q1 dash by Q2 dash is equal to C1 by C2. Okay. So ratio of charges on the bodies or on the capacitors is equal to ratio of their respective capacitances. Okay. So this is about the redistribution of charge. Okay. Then see, when charge is transferred from one body to another body due to potential difference, then what is done? If charge is transferred from the body at high potential to the body at low potential, when charge is displaced, then common potential is established finally. So, due to sharing of charge, work is done, because this is the conducting part, conductor. When charge moves, when charge flows, then work is done against the resistance of the conducting part. Okay. So there is loss of energy. So if work is done against opposition means resistance, then energy is lost. Okay. So what is energy lost in redistribution of charge? Next derivation. Okay. See, we have already taken two bodies, and when the bodies are connected by the help of a conducting wire, then charge flows. V1 greater than V2, charge flows from the body at high potential to the body at low potential till potential becomes same. So before they are joined, okay, before contact, we have not used any wire, connecting wire, okay. Before contact, total energy of the capacitors or of the charged bodies. So as we know, formula for energy, we use this formula, half CV square. Then for this body, energy is half C1 V1 square. For this body or for this capacitor, as we have taken, energy is half C2 V2 square. So total energy, half C1 V1 square plus half C2 V2 square. Okay. So this is a general formula for total energy. C1 V1, C2 V2, then half C1 V1 square plus half C2 V2 square. Okay. After contact. So when the bodies are connected, then charge flows from the body at high potential to the body at low potential. Potential becomes same. Or if we use parallel plate capacitor, then potential difference between the plates of both capacitors becomes same. Okay. So V is common potential. After contact, total energy. Like this is taken as E1, this is taken as E2. Total energy before contact is E1, total energy after contact is E2. Then after contact, total capacitance is C1 plus C2, as we have discussed. Both the bodies or both the capacitors attain common potential, so the body's equivalent capacitance is C1 plus C2, and potential is V, which is common, then V square, half C V square. In place of C, we do take C1 plus C2, means total capacitance, since both have same potential, total capacitance is C1 plus C2, again in the same form, half CV square. This is initial energy and this is final energy. This is energy before contact, this is energy after contact or after connection, what we may say. Okay. Then which one is more? Energy before contact is more or energy after contact is more? See, when the bodies are brought in contact by the help of a conducting wire, then only charge flows from the body at high potential to the body at low potential. Then energy is lost since work is done. So obviously, total energy before connection is more than total energy after connection, because the energy is lost when charge flows, and so long as there is no flow of charge, means before contact, total energy is more as compared to total energy after the bodies attain common potential, means after the flow of charge, we may disconnect, both the bodies attain same potential V. So total energy after contact is E2, which is less. Total energy before contact is E1, which is more. Then it's very easier. What is loss of energy? Okay. What is loss of energy? This is formula for common potential. We know it. This is formula for common potential. Then loss of energy. Loss of energy. Loss of energy. Loss of energy, let's take delta E, that's equals to initial energy minus final energy. Okay. Energy before contact minus energy after contact is equal to loss of energy. We have taken E1 minus E2 since E1 is greater than E2. E1 is greater than E2. Okay. So, just use the formula. we have already found all the formula, means respective relation C1 and E2. So delta E is equal to E1. Total energy before contact, half C1 V1 square plus half C2 V2 square. Total energy after contact, half. Total capacitance is C1 plus C2 and common potential is V, half CV square, right? So delta E is equal to half C1 V1 square plus C2 V2 square. We have got half common minus half C1 plus C2. Total capacitance V. V is C1 V1 plus C2 V2 divided by C1 plus C2 whole square. Formula for common potential C1 V1 plus C2 V2 divided by C1 plus C2. Okay. Delta E is equal to C. This is C1 plus C2. This is C1 plus C2 whole square. In one step we will do it whole square divided by C1 plus C2 whole square. So this cancels square. Okay. V is C1 V1 plus C2 V2 by C1 plus C2. V square means C1 V1 plus C2 V2 whole square divided by C1 plus C2 whole square. See, V is equal to C1 V1 plus C2 V2 divided by C1 plus C2. So V square, in place of V square, we may write C1 V1 plus C2 V2 whole square divided by C1 plus C2 whole square. So this is C1 plus C2, this is C1 plus C2 whole square, thus square is cancelled. Okay. So finally, delta E means loss of energy, half C1 V1 square plus C2 V2 square minus half C whole square. We may take whole square directly. C1 square V1 square plus C2 square V2 square, okay, plus 2 C1 V1 C2 V2 divided by C1 plus C2. Okay. First bring half common. First bring half common. Half and half. Bring it common. Bring it common. Okay. Then delta E. Derivation is longer but easier. Just after deriving, you just remember the final formula for application in numericals. Okay. Half LCM C1 plus C2. LCM C1 plus C2, then multiply. C1 V1 square plus C2 V2 square into C1 plus C2 minus C1 V1 square plus C2 V2 square plus 2 C1 V1 C2 V2. Okay. Now, very easy. Half. First multiply C1, then multiply C2. First multiply C1. C1 square V1 square plus C1 C2 V2 square. Then multiply C2. Then multiply C2 plus C1 C2 V1 sorry. Okay. C1 C2 V1 square plus C2 square into V2 square. Okay. If you multiply, we will get like this. Then open the bracket minus C1 V1 square minus C2 V2 square plus 2 C1 C2 V1 V2 divided by C1 plus C2. Okay. See which one is cancelling to others. C2 V2 square. Okay. Okay. Here we have not taken. This is C1 square, C2 square. Okay. C1 square, C2 square. Okay. C1 square, V1 square, C2 square, V2 square. Okay. So C2 square, V2 square, C2 square, V2 square get cancelled. Then C1 square, V1 square, see this is C1 square, V1 square minus, this is minus C1 square, V1 square, this is also C1 square, V1 square, get cancelled. Then total loss of energy delta is equal to half. What it comes? C1, C2, V2 square plus C1, C2, V1 square plus 2, C1, C2, V1, V2 divided by C1 plus C2. Then delta I, loss of energy is half. C1, C2, C1, C2, C1, C2, bring it common. C1, C2. Inside the bracket, again, C1 plus C2. C1, C2, C1, C2, C1, C2, bring it common. Then divided by C1 plus C2, then the remaining factors inside the bracket, V2 square plus V1 square. This is minus, this is minus. This is bracket, negative, this is negative, this is also negative. Okay. Then the remaining factor is 2, V1, V2. Okay. Then result is finalized. Loss of energy, I will write here directly. Loss of energy delta E is equal to C1, C2, C1, C2 divided by 2 into C1 plus C2 divided by 2 into C1 plus C2. Then this is V2 square plus V1 square, or you may write like this, V1 square plus V2 square minus 2 V1 V2, and we may write it V1 minus V2 whole square, V1 minus V2 whole square. Okay, this is formula for loss of energy. Just remember this final formula. Derivation may be longer, so it is usually derivation is required in board level exam, or if any exam in your school level exam and board level exam, but not required for competitive. This derivation, just use this formula for loss of energy in numericals. Okay. So this is about sharing of charge, the redistribution of charge, and loss of energy due to sharing of charge. Okay. This is the end of lecture. Thanks, children. I will meet you again with some beautiful concepts. Thanks.